Okay, good afternoon, folks. So this is lecture 22, and this is our last new lecture for the course. So this will be the last time I'll be presenting anything that's new for you. And just to remind you what's ahead, on Monday of next week, we'll hold a Q&A for Lab Assignment 5, so ask me anything. And if no one has any questions, we'll terminate the class early. I tend not to get many questions at those, so that session can be a good occasion for you to get some focused attention on whatever problem you might be having. So that's the story with Monday, and then on Wednesday of next week, we'll do a review for the final exam. Okay, now let me just tell you about the final. So it'll be like the midterm in format. It'll be a Moodle exam, open books and book and notes. And you can take the exam at any location you prefer, right? So wherever you want, you can take it. In the designated room, or you can take it in your dorm or wherever. And it'll be comprised of a set of multiple choice problems, just like the midterm was. And it'll cover the material from the entire semester, but there'll be a bit of a greater emphasis on the material that happened after the midterm. And of course, I'll remind you of academic honesty. Don't collaborate with anyone, and don't use Chegg or anything like that. If you need additional time accommodations set up on Moodle, then just let me know via email, and we'll set those up. Okay, so that's the story with that, and then we'll be finished with this course. Okay, so today is going to be a relatively short lecture, and I'm going to cover the topic of interrupts and contrast that with polling, which I'll define for you. And this is sort of the last piece of the puzzle that you need for solving the piezo speaker part of lab assignment number 5. Okay, and so let me just set it up this way. So I just sort of start out here with an analogy, nothing to do with embedded systems, but I want to contrast polling, which we've been doing, with interrupts. And so let's suppose that tonight something really important is going to be happening on TV, whether it's the Sox playing the Yankees, or it's World Cup, or it's a great episode of Seinfeld or Friends or whatever you watch nowadays. But whatever, something really great that you want to watch, and your friend wants to watch it with you, right? And so you have a plan that your friend's going to stop by your place to watch TV with you, right? But you don't know quite when they're going to arrive. They'll get there as soon as they can, but probably after the show has started. Okay, so what do? Do you, on the left side, do you sit down and start watching TV? Right, and you're enjoying your show, eating your popcorn or whatever, and then do you stop watching, and do you walk away from the TV and go over to the door and stand there at the door and wait for your friend at the door, and you're waiting until they show up, and then when they get there, you together go back and watch TV. Okay, do you do it that way? That would be what we think of as polling. You're at the door polling, and you're waiting. Is my friend here at the door? Is my friend here at the door? And you keep waiting for your friend. You're polling, you're sort of interrogating the door to see if your friend is there. But of course, while you're doing that, you're not watching TV. Or do you do B? Do you tell your friend, you text your friend and say, hey, listen, of course, when you get here, just ring the doorbell and I'll come get you, right? And then you start watching TV. And then you're just sitting there watching it, and you're liking it. Right? And you're watching and watching, then ding dong, you hear the doorbell, you interrupt your watching, and you go and you handle that interrupt, right? You stop watching, you let your friend in, right? Hey, glad you're here, let's go. And then you go back and you return from that interrupt, and you return to watching TV. Well, that's what you do, right? That's what we would tend to do. That's how doorbells work. So that's the notion of an interrupt versus polling. And when you're polling, you're just sitting there waiting and waiting and waiting and waiting and waiting, and you're tied up and you can't do anything else because you're polling that door. Whereas you set up the doorbell to serve as an interrupt, you literally interrupt watching TV. You go service that interrupt, let them in, and then you go back to watching TV. And it's this interrupt that I want to teach you about today. So Here's sort of a pseudo-code-ish way of defining this, right? So in polling, like that first case, so let's take a look at this pseudocode, right? So there's a while loop, right? And maybe you're doing some stuff, and then you do some more stuff. And now you're going to go and you're just going to wait for something to happen, something, whatever it is. You're going to wait for it to happen, right? And look at this construct, while wait for thing equals 0, semicolon. And we've had that statement in our code for a couple months, right? And you have while followed by a semicolon. That what's going to happen is the processor is just going to be tied up waiting, right, for thing to be equal 0. And until thing equals 0, the processor stays right here, and it's executing that null command, which is the semicolon. So it just stays there, waiting and waiting and waiting. And if wait for thing, if it stays equal to 1, right? If it doesn't equal 0, then the processor will just continue to execute this command. It'll wait there forever, right? And and then finally, once wait for thing goes to 0, then you can do this command and you can go back to the loop again and repeat. That's called polling. And what you're doing is you're polling this particular variable here, waiting for it to equal 0. And until it equals 0, you're just sitting there waiting, and you've got the CPU, you got the computer, you got the microprocessor inside your 328P tied up. You can't do anything else while it's waiting. Okay, and that's how we've been coding all semester long. We had that in there when we were, it's part of the UART. We wanted to wait until some UART register was empty, and of course it happens fast, so we don't notice the delay. We have that in the analog to digital converter, because we have this thing called a successive approximation analog to digital converter, and so we polled this pin to wait for the analog to digital converter to be done converting. And now we've been using this when we're setting the timers. And the implications of this when we are setting timers and doing fast things is going to become obvious to us. And so I'm going to show you a case where when, playing tones into a speaker, for example, that this becomes a problem. It's because we want to do some other things while we're busy polling, and we can't. So that's the issue. Okay, I've got a question. Is it considered polling if we use the delay millisecond? That's a different thing there. I mean, the delay millisecond function, it goes off and it waits, for the amount of time that we specify. And how that's actually implemented, it's not interrupt driven. It's actually wasting time, the amount that we specify. So it's a little different. Someone has just answered it. We're just waiting in that case. Okay, but now let me show you the sort of the polling, the interrupt example. Okay, so the very first thing is we're going to enable this interrupt called thing. Right, we're going to enable the thing interrupt, and we're going to create this program down here called the interrupt service routine. Okay, and that will specify what happens when we get the interrupt. And so now we get into our loop. We're going to do some stuff, do more stuff, do even more stuff, do more stuff, and loop again. And we're free to keep doing this, and we just keep doing it again and again and again and again and again. Wherever we happen to be, when thing happens, we'll jump out, come down here. We'll handle the interrupt. We'll take care of it however we programmed it. And then we'll come right back and continue what we were doing. So we're allowing it to interrupt what we were doing. Now, you can get into some complexity here in setting interrupt priorities, which piece of code is allowed to interrupt what happens if you have multiple interrupts, things like that. Let's not worry about any of that. Let's just here look at the very first level of interrupt. You're doing stuff, and you're either going to poll something to wait for something to happen, or you're going to, work with an interrupt, which just means you're going to enable the interrupt, and you're going to set up what's called an interrupt service routine. And I'm going to show you some examples of that, and then I'll show you how it's useful and why you should care. So this first example, I just wanted to show you, review something that we've been doing already all along. I've just got an LED that's blinking at 10 hertz. Okay, and we've been first. Let me just run it so you can see it. Look in the top right. And by the way, this here is called an explained mini. It's a development board. That's what we used in 231 last year. This semester we used the Arduino, and then we went to the Bear chip. Last semester we used this device, but we had some problems with it, and that's why I moved away. But I had built this example code for that device. But let me just show you. I mean, when I let the movie run, you'll see an LED blinking at 10 hertz. Okay, nothing fancy there. But let me just walk you through how this code works, and I'll just point out where we're doing the polling. Okay, so what I've got is an LED that's connected to pin PB5. So here we're just setting PB5 as an output pin. And then here I'm initializing a timer to be in normal mode with a 1024 clock prescaler. And then the math for the timer is all down here. So I won't go through that here. If you're interested, you can look at it later on. But once we get into our loop here, what I do is we load the timer with a certain value, and then we let it count up until it reaches the top and overflows. Then we reset the overflow, toggle the LED, and then we loop again. Okay? So I'll say it all again. After we've initialized the timer once, which means we just have it set as a free running timer, normal mode, it's counting up, and it's using this 1024 clock prescaler. Okay, and we get into the loop. The first thing we do is we set the timer control register to this initial value, and what that will do is it'll allow it to to count up to 1/20th of a second, so that the LED is. Then we're going to toggle the LED. It'll count up to a 20th of a second again, and in so doing, we're causing the LED to blink at a 10 hertz rate. But the principles here were, after we initialize that counter, we preload it with a value, we let it count up until it bangs into the ceiling, until it overflows, and now we're polling all this stuff, waiting for that overflow. And this is the key. While we're waiting, nothing else can happen, right? It's where that semicolon means you're just executing a null statement. You're just in that while loop, waiting and waiting and waiting and waiting and waiting for for 1/20th of a second, and then once the overflow occurs, we leave the while loop. We clear the overflow flag. That's just something you have to do. I call that a quirk in the AVR family of microcontrollers. We toggle the LED and we loop again. Okay, so it just gives us that 10 hertz blink. Now I'm going to show you the same code where I rewrite it using polling. Using interrupts instead of polling. So let's go and look at that. Same code. Let me run it. There's your 10 hertz. So the LED and our eyes aren't going to know the difference here. Okay, but let's just take a look at the coding here. I'm setting the output pin. I'm initializing the counter, and then this is where it gets different. I've got these two things are enabling the interrupt. This is like when we told your friend, hey, when you get to the apartment, just ring the doorbell, right? And this is what's happening over here. There's a register called TIMSK1, right? Timer counter 1 interrupt mask register. So it's the timer interrupt mask register, and it's 1 for timer counter 1. I mean, they got all these acronyms in there, and there's a bit in there called the timer counter 1 overflow interrupt enable, right? And when we do this, when we set the timer counter 1 overflow interrupt enable bit of that register high, we are enabling the interrupt. Okay, so that's just telling the processor, when this thing overflows, go and handle the interrupt. That's what this does. So all of this, its purpose is to set up an interrupt. So that we're going to have code running in the background, right? But then when this interrupt occurs, because we've enabled it with this, then we're going to go off and we're going to service the interrupt. Now, one more thing you have to do is enable the global interrupt. This is, you're going to tell the processor to allow interrupts to occur, and there are lots of different kinds of interrupts. We're using the interrupt in the timer, but there are other kinds of interrupts. And this command SEI, you just need that to enable interrupts to occur. So we do all that. This is just in the manner of setting everything up. We've set up the timer, caused it to start counting, and we've enabled the interrupts. And now look, we're just sitting there. We're doing nothing. Our while loop here is doing nothing. We're just idling, right? We're wasting time. I'm going to show you another example where we're not wasting time, right? But we're not toggling our LED in here. We're just our while loop here. Let me jump back to the previous slide. Okay, so jump back. Right? And it was in the while loop that we were monitoring the counter and we were toggling the LED. Okay, but in this code, in our while loop, we're not doing anything. Right? We could do something, but we're not. And what's happening is all of this stuff will cause the timer to start counting. Whenever it overflows, we'll jump down here to the interrupt service routine for timer 1. Once we get in there, we reload the counter and we toggle the LED and we jump back out. Okay, so I'm going to show you the next slide. I'm just going to show you these two pieces of code side by side. Oh, here they are. Okay, so you've got what you've been doing so far, which is polling on the left, and then I've rewritten it on the right with interrupts. And so one of the things that you can see is to do it with interrupts on the right, you have a new construct. You have to have this interrupt service routine and you have to set some enables, right? So it's more complicated, right? You have to use more of an advanced programming. So why do we do it, right? Why do it that way? Well, I'm going to motivate this by showing you what happens when we want to make tones, right? Audible tones that we can hear, and what happens when we use polling versus interrupts, okay? So these two examples were just for blinking lights, but let me go and show you a piece of code here that I wrote for you, and it's called tone ramp, right? And the idea, what's a ramp? If you walk, you can walk up a ramp or down a ramp, right? The idea is I want to ramp up the frequency being played to a speaker. So that's why I call it a ramp. So I'm going to increase the frequency of tone played to a piezo on PB0. And I'm using timer 1 and I'm using polling to detect the overflow. Okay. Now the circuit here that I have, all that matters here is that I have my piezo here and it's connected via PB0. So here and here. Everything else on the circuit, this is the same stuff that I showed you in our last lecture when I was illustrating how to use the OLED, right? So we're not using the OLED in this application, but I left it there on the circuit board. So here, all that matters is I'm going to be toggling PB0, which is this pin here, and I'm going to be making going high and low, high and low, high and low, and that's going to cause sounds to come out of the piezo. And what I want to do is, where I'm going is I want to play a certain tone for a couple seconds, and then I want to play another tone for a couple seconds, and another tone for a couple seconds. All right, so I want to linearly increase that. So let's take a look at the code here. So I'm going to have a variable called frequency, right, and that'll be the frequency in hertz that we're playing. Okay, I'm going to set that the pin PB0 as an output pin. I'm going to initialize the timer for normal mode with a prescaler of 1024. Then I get into my while loop. I load the counter, and here what I'm doing here is, and you can look at the math that I showed earlier in this class. But if you take this number here, frequency, and you put it in here, that will preload that counter in such a way that it will overflow, at a rate corresponding to frequency. Okay, and so when we will be toggling a pin, using this preload value, and that'll cause the piezo to issue a tone at the frequency specified by the variable frequency. Okay, and I'm going to start out with that at 100 hertz. So I preload the counter with an appropriate value so that when I toggle it, it'll give me 100 hertz. Here I'm polling now, okay? I'm going to be polling just like we've been doing. So I'm going to wait for an overflow to occur. I'm going to clear the overflow flag. I'm going to toggle the LED, and then I'm going to loop again. Okay, so let me just run this one first. Notice that I have some structures down here that are important. Right now they're commented out. So right now all I'm doing is playing a 100 hertz tone. Okay, I'll go ahead and play it. You'll get the tone coming out of this one. Were you able to hear that okay, David?
Yes, we were able to hear it just fine in the classroom.
Okay, so all we did is we played a 100 hertz tone. That was it, using polling. And we've been doing this, for a while. Now, when I want to change the frequency, what I'm going to do is I'm going to change this variable frequency, and that'll change the preload value. Okay, so the code down here is going to allow me to do that. So I'm going to go to the next slide where I take away the comments. See, I've got a block comment here so that this code is not in effect. Let me go to the next slide, and I take that structure out. So everything here is the same, right? We're going to be waiting for the overflow, toggling the piezo. Then I go down here and I change the frequency, right? I'm going to add 100 to it. So if it was 100, it'll be at 200. And I want to do that until a kilohertz. And when it gets above a kilohertz, I want to jump that down to 100. Because what I want to do is I want 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, and then back to 100. And I want to play the tone, for 2 seconds. So I have a delay here of 2,000, right? So what I want to do here is set that frequency, play it for 2 seconds, and then I want to go through the loop again and change it. So I'm hoping for 100 hertz for 2 seconds, 200 hertz for 2 seconds, 300 hertz for 2 seconds. So let me run it, and you're going to have to listen carefully to hear it. So all you hear is a click every 2 seconds. So this doesn't work. All right? This code fails to achieve the objective. And why is that? Well, let's look at what's happening here in our loop. I'm preloading the counter. I wait for the overflow. I clear the overflow. I toggle the LED, right? I toggle the speaker. That's the click you hear. Then I go through this stuff, change the frequency. Then I wait for 2 full seconds. Nothing's happening to the piezo for 2 full seconds. So all I do is in the top half of this, right, I just cause it to click, right? Because I'm reaching the overflow at a certain rate, and I click it, right? But in order to get a sound out of it, I have to keep clicking it. Click, 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 click. I can't wait. And so the problem here is I want to put a delay in here, right? But I want that tone to be playing in the background, but it's not, right? Because this is all sort of foreground programming here, right? And so I count up, I toggle, you hear a click, and then I wait for 2 seconds before I do anything else. I go back to the top, toggle, click, right? Wait 2 seconds, right? And so let me just play it again for you. So you can hear those clicks. That's it. Okay, so the flaw here is that we've got everything taking place here in the foreground, and when I've got a delay, I'm just waiting. I'm killing time, right? And I'm not toggling that speaker, so I'm not creating a sound wave with the speaker. What we want to do is have that speaker being toggled sort of in the background with an interrupt. And so now let me show you how to implement that using an interrupt. Okay. So let's just read the first 3 lines here. I call this tone ramp interrupt. It increases the frequency of a tone played to a piezo on PB0. It uses timer 1 and interrupt. All this down here, this is just telling you how I'm determining the frequency. Okay, and it's the same material that was on an earlier slide, but this is just sort of clarifying. It's just clarifying that line there. okay? But let's take a look at what's happening. Okay, I have a delay, and I'm calling it ramp delay 2000, and that's down here, okay? Okay, I have my frequency variable here. I'm setting the output pin, PB0 as my output pin. I'm enabling the timer and setting it up the same way. I'm enabling the interrupts. I get into this loop. I have a variable called preload, right? And I'm just that preload. All that is the value that I should preload into the timer based on the frequency that I want to play. Okay. On the previous code, I was actually loading this value into the timer. Here, I'm just putting it into a function called preload. Then I'm incrementing the frequency, and I'm doing the delay. But down here is where the action occurs. When the timer reaches the top, right? We're gonna set it running over here. Once it reaches the top, it's going to jump down here. I'm going to preload it with this value that I've calculated here, and I'm going to toggle the LED. I'm sorry, I keep saying that. I'm going to toggle the speaker, and then I'm going to jump out of that routine. And this interrupt will take place. It'll interrupt whatever it's doing to toggle that piezo. So even if I'm sitting in this delay, and I've got it set for 2 seconds, even if I'm sitting in that, right, it will interrupt that waiting, come down here and service the interrupt by toggling that piezo. So it'll allow us to continue to get the sound out of it. So let me go ahead and run it. And what you're going to hear is 100 hertz. It'll wait for 2 seconds, and then 200 hertz, 300 hertz, and so forth. Okay. The next two slides are just for fun. I wanted to just show you what happens if I change this delay. This was 2 seconds, right? A delay of 2,000 milliseconds. So on the next one, I'm just going to change that from 2,000. I'm going to make it this one, 100 milliseconds. Same code. And then this is 10 milliseconds. So if you've ever sort of played a video game where you're hearing that sound, now you know where it's coming from. Okay. Any questions or comments on what we're doing here, on why we're doing it or how we're doing it? Yeah, sci-fi noises, that's right. How does the code know it's overflowed here? Okay. The code knows it knows that it's supposed to jump to the interrupt as a result of these two lines 24 and 25. So first of all, line 25 is set global interrupts. That just says this is code that's going to be allowing interrupts. Line 24 specifically says when we have an overflow, go down and service that using this routine. So line 24, when we specifically set it up, we are enabling the timer 1 overflow interrupt. Now, how does the timer actually cause to be interrupted? Well, when we issued lines 22 and 23, it started counting, right? Lines 22 and 23 are providing the clock and setting it in normal mode. The counter just starts clocking at that point. It starts running, and we set up the interrupt. We enable the interrupt here. So as soon as it reaches the top, it's going to interrupt whatever it's doing, and it's going to jump down here. It'll execute this, and then it'll return to where it was. Okay. The question is there any command or function of code that an interrupt cannot interrupt or should not? There are all kinds of things where you can get into interrupt priorities. What happens if one function interrupts another function? And should you set priorities for interrupts. And you really can get into some complexity when you're using multiple interrupts. We're not worrying about any of that here. So for your purposes, I mean, this is the way, in experiment number 5, right? What you're going to be doing in your main while loop is you're checking an infrasound sensor to get a distance, and you're displaying the distance on the OLED display. You're kind of busy doing that, right? And you may want to put a delay in there to control the loop. But you also want a piezo buzzing in the background at an appropriate frequency. So set it up this way. So in this example, the interrupt takes priority over everything in main. Yes, that's correct. The interrupt will interrupt whatever else it's doing, and it'll go off and service that routine. That's right. So, and you can think about interrupt programming as kind of a more advanced programming topic. And we're just scratching the surface of it, but it's an important thing to know that this is what you can do with one of these simple processors. Okay, and so this example ought to give you everything that you need to get this part of your overall system working, this speaker part of it. Okay, why is it called an ISR? Yeah, ISR stands for Interrupt Service Routine. And depending on the kind of interrupt, there is a corresponding interrupt service vector that you have to use. And so just like we had to use TIMSK1, right? That particular interrupt that we're using corresponds to, if you look at line 37, it corresponds to interrupt service routine with the name timer1 overflow vector. And so if you had a different interrupt that you had enabled, you would use a different name for the interrupt vector down here. And so all of your interrupt service routines are going to be handled in a function that you create called ISR, interrupt service routine. But then the actual parameter that you would give, the vector, would correspond to the type of interrupt that you're doing. And so if you take a later course where you're doing more work with embedded coding, or if you explore this in more detail in something like your senior design project, then you would get into more of this. But if you want to learn about it, you can look up interrupts in the textbook or on the data sheet, and you'll see a whole table of interrupt vectors corresponding to the various interrupts that you can set. So, folks, that's actually all the new material that I want to present. Nothing else that's going to be new in this. So that's really formally the end of the course. We've got, the Q&A session for Lab 5 on Friday. On Monday, and then our review a week from today. I'm happy to take any more questions you might have on this. But otherwise, we can call it a day. Yeah. So, question: does the service routine clear the timer? Yes, it does. In this particular case, this is one of these kind of quirks about AVR. That's a good question that you asked, Danny. We don't have to manually clear the timer overflow flag because it gets cleared automatically by the interrupt service routine. We do have to reload the counter value that what we've got in line 39 TCNT1. We're reloading it, but we don't have to clear the overflow bit, and it's because we're not polling that. We're instead of polling, we're interrupting. So we're doing it in a different way. Okay. Why don't we leave it at that? I'm going to, I'll stop sharing. I'm going to shut off the recording, but I'm going to stay on the line if you have any questions.